Hello, everyone. Thank you for joining another session, Flat and Learn Networking Broadcast. My name is Jiří Chaloupka. As we discussed, we will talk and we will focus mainly on the services overlay, but there is no services overlay without the transport. So that's the reason why I invited the very special guest today, the Jose Liste. And Jose will talk about the segment routing fundamentals. Jose will explain some of the basics of the segment routing with the focus on the MPLS data plane. So Jose, welcome to the session, and the stage is yours.
Thank you, Jiří. Thanks for the invitation. I'm glad to be in your series and be able to complement the content that you deliver to your audience over the services, and now talk a little bit more about the transport. So the topic is segment routing. And we really frame segment routing in the context of an evolution to the network. It's an evolution that is happening across service providers, large enterprises, financial companies, web operators. And maybe the best way to visualize that evolution, if we start from the bottom of the slide and you look at the data plane, what's happening on the wire? And what's happening on the wire, on the left and on the right, legacy, yesterday, today, to the right, which is today or the future, is the same thing. What I'm running is I'm running MPLS as my data plane. So my devices are performing basic label-based forwarding functions. They're doing a pop, they're doing a push, they're doing a swap. Now, the big changes are happening, what's happening on the transport protocols. If you look at what most operators today have in their networks, obviously you need to have an IGP to serve as your routing protocol. You're running another protocol to signal and exchange labels. So you have your intra-domain LSP signaling, majority of people relying on LDP. Then you throw one more. If you want to do some fast reroute, most likely you are using RSVP for that, or you might also be doing intra-domain LSP signaling with RSVP. So our number of protocols is what it is on the left-hand side. If you look at the right-hand side, which is what we're doing with segment routing, is we are simplifying all that protocol mix that you saw on the left, and everything is being reduced to an IGP itself. So the IGP has been extended, so we call them the SR extensions. So now, obviously, you continue to do routing, but now you can signal your LSPs. These are your intra-domain LSPs, and the IGP can make use of the properties of SR to also do your fast reroute and your path protection in the IGP. And as well, you can use the IGP database morphed into AT database to also do your intra-domain traffic engineering. So big changes from the left to the right when you look at the transport. Now, for those of you operators who have larger networks or multi-domain networks, today you probably use a design with BGP labeled unicast, BGP LU, also called seamless MPLS, where BGP on top of the intra-domain LSP signaling, BGP can signal also the inter-domain LSPs. If you look at what we're doing on the right-hand side, you have an opportunity to augment BGP-LU or to replace BGP-LU with a function. It's a path computation element. A segment routing path computation element can be also used to signal and to compute inter-domain LSPs. Perhaps your best step for LSP is signaled by BGP-LU, and your inter-domain LSP with SLA is signal with computed by the SRPC. Now, what happens on top of the transport is what Jiří has been talking to you about, is where today you probably, or yesterday, people were using different set of solutions for layer 3 and layer 2 services, and now being able to unify the service layer with BGP. And BGP directly will offer the L3 and the L2 services. Obviously, in today's session, we're not going to talk about that upper layer. This is the topic for Jiří and his further guests, but it will actually showcase the fact that the service layer will now ride on this transport layer that on the right-hand side has been simplified with the objectives of SR. Okay. At the end of the day, you realize a network that at the transport, it has less protocols. It is simpler for the device to operate from the protocol mix, and it is easier to troubleshoot from your people in the NOC. We are giving you, with segment routing, you have a solution that maintains intelligence in the network. The routers can pre-compute a backup path for 50 millisecond protection. The routers can compute a traffic engineer path. At the same time, if you wish, you can also enforce centralized optimizations. So it's neither fully distributed, fully centralized. It's really up to you how much you want to be in the middle or how much you want to be on the left-hand side or the right-hand side. At the very end, it's very important, as you will see, we are relying on a network that now no longer keeps state. We are looking at a stateless IP fabric where you are free to deploy traffic engineering and the deployed application-aware forwarding where you're not imposing any state in the middle of the node. Obviously, all of these factors allow for devices who are actually inherently simpler. So you're doing simpler devices with higher and richer behaviors on the network as a whole. And we go into the why segment routing and at a very broad level, some of the use cases for segment routing. So you can see I'm trying to put in the columns the different technologies by which somebody would have enhanced or improve an existing MPLS backbone, or a way how somebody will go about building a new MPLS-based backbone. So with SR, and you will see the different rows, what we're trying to hit is the mark on simplifying the operation of the device, simplify the operation of the network. We're looking for a network in 20,000 in 2020, the network that is IP friendly, a network that maximizes the use of equal cost multiple path, a network that is able of computing backup path and is able to guarantee that a backup path can be programmed, a network where we can now deploy traffic engineering with ease. And this is one point that we always take. With SR, we are democratizing TE. So TE is no longer a topic that is only for the operators who have a large number of CCIEs or experts or PhDs. No, anybody can implement traffic engineering with SR. It includes cases that can cover multi-domain for the complex networks. And if you look at the next 3 rows, we bring the concept of intent. We want you to be able to put intent into a service route like EVPN route and be able to honor that intent in a particular transport SLA provided by SR. It could be a network slice, it could be a transport path that is built on demand with ODN, and a path that is completely automated where you can put traffic directly onto the path with the properties of automated steering. So, so you get the idea as to why is SR catching so much interest from architects, for those of you who are evaluating SR, and obviously there is a large number of people that have already deployed SR. I'll give you a view on that in a further slide. So going into the technicals of segment routing, which is our topic for today, the first thing that we have to acknowledge is with SR, we're doing source routing. Source routing is based on the concept that I want to impose at the source all the instructions on how to move the packet through the network. If you look at the drawing in the yellow, is the expression of the path is put right at the source of the network. So this particular node on the top left-hand side, so that the packet can move through the network. Now the set of instructions can be instructions that will keep me in the shortest path, as indicated on the gray line, or it can be a traffic engineer path, different than the shortest path, but still reaching the destination on the right-hand side. By using source routing, what you obviously will realize is that the devices in the middle of the network, they don't really know if they're being a midpoint for somebody's shortest path or if they're being a midpoint for somebody's traffic engineering. So if you look this node here in the middle, it could be that these orange lines, I may have 1,000 of these traffic engineer paths going through me. I may have 10, I may have 1, I may have 1 million. It doesn't really matter. For this device in the middle, he will only look at the instruction that is coming into him on the on this yellow portion, and he executes the instruction and delivers the packet. So you really have a unbound and scalable infrastructure that can deliver any type of transport, SLAs. So from a data plane perspective, going deeper into the concepts, when I say putting the path expressing the packet, what do I mean? Well, we really talk about the semantics of the segment. So the segment of segment routing. The segments are basically, when we use MPLS as a data plane, the segments are MPLS labels. Okay, so my segment is an MPLS label. When I look at an IPv6 data plane, which is another sibling of SR, then your IPv6 addresses will become the segments. In today's session, as Judy indicated, we're going to focus on MPLS, and pretty soon we're going to have sessions coming up where we're also going to talk about SRv6 in this forum. In the control plane, what we have done, and this is what I indicated earlier, we have actually kept the power to the IGP protocol, so whether it is ISIS or SPF as your flavors of IGP or BGP, and we have extended them to allow the possibility to signal also the label for a particular prefix. On the right-hand side, you will also see that there are protocols that have been extended that allow for the centralized intelligence with SR. So BGP has been extended. Path computation element protocol has been extended. And obviously, programmability ways like netconf-yang are there to take advantage when you program a segment routing network. It is important to mention at this point that segment routing has not introduced a single protocol into the protocol stack at the IETF or into anybody's network. Segment routing's goal has been to remove protocols from the network. And then, as we mentioned earlier in the picture, the paths that I can use in SR for majority of people or majority of the traffic will be my shortest path. But if I want to have a path that is traffic engineer, then you have to think about a path that can be computed by a router, a path that can be computed by a central entity, or a path that is just given by a human and it's an explicit path. So for those of you who were not keeping track, SR is no longer the new kid on the block. SR has been around from inception since 2013. So we're now in the 7-year anniversary of SR when Cisco went to a public conference and said, hey, we have an idea. And the idea is let's bring source routing to IP networks. And let's do it with MPLS to start with source routing. A few months after that, I would say 9 to 10 months, there was already an IETF group dedicated for standardizing extensions and documenting the architecture and the use cases related to SR. Fairly quickly after that, in the fall of 2014, Cisco was already shipping SR in the iOS XR operating system. 12 months after that, in 2015, we were already having the very first of customers deploying SR. So the customers who are running SR with Cisco Live in production have already been doing that since for over 5 years. SR is also a reality for not only iOS XR, but it's also in iOS XE and in Nexus OS. Currently, we're tracking over 200 customers where SR is deployed in field trials, in lab trials, or architectural commitments. And if you look at the right-hand side of the slide, we have actually of the first SRv6 live deployments. So we'll leave that for another topic. So talking about the technicals of SR, and it's really all about segments. And you know that in this particular discussion today, we're going to talk about the segment routing MPLS flavor of SR, and the segments are MPLS labels. So we're going to look at the control plane of how do I signal in my IGP or in my BGP, how do I signal the label values? So we introduce a concept of a segment that can be global or local. A global segment is a segment that is any node in the segment routing domain understands. It's an instruction. Let's say I'm trying to send traffic to GD, and GD has a label that is associated with his prefix, his loopback prefix. And then if I need to send traffic to GD, every router following the shortest path is going to program in its fib the label of GD, and that's a global segment. Everybody understands and everybody programs in their forwarding table. The global segments, GD's MPLS label value is allocated from a user control block of labels. It's called the segment routing global block, in short for sRGV. Okay. Then the local segment. Local segments are segments that only the node that originates the segment or the node that hosts the segment understands it and programs it. So it is now it's an MPLS label. Imagine that I have a connection to GD and I have an IGP adjacency, and I want to allocate a label to represent the adjacency that connects myself to him. That label will be programmed only by me, and therefore it is a local segment. So if we look at how these global or local segments are signaled in the control plane, then we have to start with the obvious one, which is the IGP. How and what type of semantics or segments is ISIS and OSPF able to signal? And there are two types of segments that are signaled by the IGP. The fundamental ones are the prefix segments and the adjacency segments. The prefix segment is a segment that is fundamental, is a segment that has a semantics of following the shortest path. So imagine you have a router number 4 here in the picture. That router has a loopback 4.4.4.4/32, and now you have a adjacency. I'm sorry, you actually have a label value. Actually, let me remove the timings on the slide. Sorry for that. They don't advance without my request. Okay, so I have router number 4 and I have a prefix and a label. So the semantics of that label will be such that any router in the topology, after they compute SPF, they're going to impose that label to get to the node along the SPF path. So if I want to send traffic from 5 to 4, I will send the traffic over my directed link, and when I push the label 16,004. If I want to do it from 2, I also have an SPF, and then I know how to get to 4. Now take a look at 3, the same thing. If I look at 1 has ECMP to 4, so I can send the traffic via 2 or via 3, and I will impose the label 16,004. As you can see, everybody is imposing the same label to get to node 4. That's why the prefix seed is now represented by a global label value. That's why the prefix seed is a global segment. Everybody programs the instruction to get to 4 in their fib. Number 1, number 2, number 3, number 5, they all program the forwarding entry for that label 16,004. That label value is advertised by ISIS or OSPF when 4 advertises its loopback. The second flavor of an IGP advertised segment is the adjacency segment. So imagine that, for example, routers 2 and 4 have an adjacency. So have an OSPF neighbor or an ISIS neighbor. What the router will do now is it will actually allocate a label that represents the adjacency. So in this example, between 2 and 4, the router number 2 will allocate a label with a value 24,024, and that label value will be programmed only at 2 in its fib, and the semantics of that label will be, if I receive traffic at 2 with the label 24,024, I'm not going to do an IP lookup. I'm not going to look at the shortest path of anything. I will simply pop the label and push the traffic on the interface to 4. That is what an adjacency segment will do. If you expand the concept, if I have an adjacency between 2 and 5, I have another label that represents the adjacency to 5, and the router again will if I receive traffic with a label, I will pop it and send it to 5. I'm really pushing traffic on interfaces that otherwise you could imagine that the IGP will not be able to push because maybe the metric is too high. So I mentioned the adjacency segment is a perfect example of a local segment. It is only programming the FIB at 2. However, every router in the topology knows about the label value. 2 will advertise in ISIS or SPF the fact that it has an adjacency between 2 and 5, and it will advertise the label value that it has allocated for that adjacency. So every router in the IGP database knows about the label of the adjacency, but only 2 will program it. Therefore, the adjacency segment is a local segment. And also notice that the adjacency segment, in this case with the label value 2425, is not allocated from the sRGV. So the segment routing global block is only used and reserved for global segments, and the adjacency segment is not one of them. We move on and we go into a special type of prefix segment. What happens if I have 2 devices in the network, like 4 and 5, who have another prefix configure besides their loopback and besides their dedicated loopback, and now it is a common prefix like 1.1.1.100, and that is configured on node 4 and node 5. So we call this Anycasting for IP. That's no problem with that. Well, now with SR, you have the ability of having 2 routers that advertise the same prefix and also advertise the same segment routing label for that prefix. In this example, we use the label value 16,100. So now what you're going to have, the IGP will advertise within this domain that I have in the middle, it will advertise, hey, I have 2 routers which are advertising the same prefix, and they're obviously putting the same label value for that prefix. And it's now really up to the IGP and the SPF to see, well, who is my closest? If 5 is my closest, then I'm going to send traffic. If I impose the label 16,100, I'm going to send my traffic along the SPF to 5. Obviously, if node number 5 were to go away, the IGP will inherently have in its database the fact that node number 4 also advertises this prefix with the label, so the traffic will inherently also go to 4. What happens if I am at the same distance between 4 and 5 from the perspective of 1? Well, then the router will load balance traffic towards 4 and 5. That's your Anycast segment. It is basically using the prefix segment, and the original one, we call it the node seed, when the prefix seed represents the node, like I showed you earlier in the example 4. And here you have a prefix segment that represents an Anycast for a prefix on 2 routers or more. We call that the Anycast segment. Well, but not only IGP can signal segments, also BGP can. And now we go into what we call a BGP prefix segment. It's basically a prefix segment identifier or BGP prefix seed advertised in an NLRI. For those of you who are familiar with BGPLU or label Unicast RFC 3107, what was done at the IETF is we have added an extension to 3107, and the extension is basically a BGP prefix seed attribute. And with the attribute now, when you signal a prefix or you advertise a prefix in BGP and you allocate a label for that prefix, you also advertise a SR property of that prefix that will allow any other router in the topology to allocate a label value for that remote prefix from the sRGV, the segment routing global block. So, as in the previous case where I was showing you that in the IGP, a prefix segment can be signaled and you could end up with a global label value for a IGP advertised prefix, you can also end up with a global label value for a BGP advertised prefix. When we use the BGP prefix segment, we called this BGP SR. From the control plane, we rely completely on the NLRI from RFC 3107. And the last segment in this recap is going to be the BGP Peering Segment. If you look at the Peering Segment, it's actually commonly used for a use case where we do egress peering engineering. Imagine you have a network like at router number 4. That router number 4 is the last router in your control, and then after that you connect to your outside peers, to your transit SPs, and you typically will have an eBGP session with them where you're learning routes from the internet, and you may exchange with them routes as well. In this particular case, and very in the same goal as the IGP Adjacency SID, anytime you have an eBGP neighbor where you enable the BGP Peering Segment, the router number 4 in your control will also allocate a label for that eBGP neighbor. So in this example, let's say is the label 24025. That is the label that represents the eBGP neighbor to 7. So if router number 4 were to receive traffic with the label 24025, he will pop the label and send the resulting traffic to the over the interface where you have built the eBGP neighbor with node 7. Obviously, for these cases, you are not running MPLS with your external transit, so you just do a pop and you send the on label or IP payload down to the device number 7, and that's how the EPE label can help you achieve a use case. If you could imagine that, let's say you have a prefix advertised by 7, and when it's advertised into your network, any routers in your domain, let's say router number 12, BGP best path, may choose node number 5 as the exit point of the traffic. And that's really, of course, you can apply BGP logic to alter that, but hey, you're comfortable with traffic leaving 5 for that prefix advertising 7. But what happens if you wanted to override that? And you don't want to do it for all the traffic, or you don't want to further tweak BGP? Can you have some traffic actually leaving via 4 instead of 5? And can you actually even go further, make it go via 4, and specifically via an eBGP session that 4 has towards 7? So the EPE segment will allow you to send the traffic on a particular peer, and the prefix segment from the previous case I explained, you can direct the traffic to 4. And this type of logic that I just explained is going to make me explain a very important concept. Can I combine multiple segments? Remember at the beginning of the presentation, we were talking about that path being expressed at the source. Well, the path is segments, and segments can be singular or it can be plural. So you can add multiple segments to the label stack. So now you will have a stack of labels, and when you have a stack of labels, it will be an order stack of labels. So you will impose the labels in the proper order that will allow you to direct the traffic over the path that you desire. So imagine that in this example, I have a topology where router number 4 has a prefix SID in green. So that is his node SID with the label 16004. And then router number 4 also has an adjacency SID representing the adjacency between 4 and 5 with the label that we have shown in purple. What would have happened if node 1 is instructed to push the stack of labels in the order shown? Top of stack, label 16004, following stack, the adjacency SID 24045. When you do that, you are going to instruct the packet based on the first instruction to follow the shortest path, ECMP aware path to 4. So the traffic will go to 2, the traffic will go to 3 because ECMP in the IGP, and it gets to 4. Very importantly, and as we will show in a moment, routers number 2 and 3 will basically pop the green label because they are the PHP on the LSP towards 4. So the packet will actually arrive at 4 with a single label, that's label 24045. At this point, 24,000 node number 4, when looking at the label 24,045, he will pop it and send the IP packet in gray directly to 5. So what we have done with this very simple example is show you how do we do traffic engineering with SR. The source will impose a stack of labels, and the stack of labels will tell me how to go through the network. Now, the question that you obviously will have now is, how did one realize that he wanted to push these 2 labels to get to 5? Who came up with that decision? And again, here, what you had realistically is a traffic engineering problem. I want to go from 1 to 5, avoiding the connection between 2 and 5. Because if I go to 5 over the shortest path, I will go via 2. But for some reason, maybe the link between 2 and 5 is unreliable. Maybe the link between 2 and 5 has a high cost. Maybe the link between 2 and 5 is a transatlantic link, or maybe it's going through a region that I want to avoid. That is a problem. The problem now is expressed to the router, and either a human configure that explicit set of instructions, or maybe you to compute the path based on the problem. Or if this were needed, you can ask a central point to say, hey, help me out. Can you compute a problem to avoid the link between 2 and 5 coming from 1? So, but the outcome of the path computation, or the explicit path that the human provided, is expressed with a stack of labels that is imposed at 1. The other takeaway to take from this is, I'm not pushing a label per link that I need to traverse. That would be against the objective of SR, which is using the ECMP and the richness of the network. As you can see, I want to go from 1 to 4, and I want to use any ECMP between 1 and 4. So I'm not pushing adjacency seats that 1 may have between 1 and 2 and 1 and 3, and then adjacency seats between 3 and 4 and 2 and 4. No, I push the prefix seat to get to 4, and that will give me that ECMP rich path to 4. And then, because I really want to force the traffic between 4 and 5, let's say 4 and 5 was a high IGP metric link, I have to force it there. So then here I use an adjacency seat. So here you go. Here's how you see the SRTE in action when looking at the data plane. Well, let's talk about data plane briefly in the remaining minutes of our talk today. In the data plane, in SR MPLS, everything is about MPLS operations. So the segment is an MPLS label. The segment list, which is the path or the set of instructions, is a label stack. But everything is label operations. Everything is a pop. Everything is could be a pop, a push, or a swap. Routers who are able to perform the functions that you well know, such as PHP, if you're the penultimate router, or if you want to maintain the label all the way to the end, you can also use explicit null functionalities. That is it. And sometimes actually people get confused and ask me when they think SR, and I say, hey, SR uses MPLS, they think that SR label is something different from the MPLS label. No, the SR label is the MPLS label. When you look at the structure of a label, the MPLS label, the 20 bits for an MPLS label is the same label that we use in SR. There is absolutely no changes in the data plane for SR MPLS. And that is why, in retrospect, if you go back to 7 years ago, that is why SR MPLS has been shipping for 5.5 years now, because any router who could do MPLS operations can do SR. So pictorially, if we actually take a look at how it looks, imagine you have a router number 4, which is advertising his loopback 1.1.4, and the loopback also has a segment routing prefix seed 16004. Imagine that I'm running an IGP. So router number 1, 2, and 3 will learn that router number 4 is originating the prefix 1.1.4, and that prefix is has an associated label of 16004. Who configured that label? Well, that label is now part of your responsibility. So You configure the loopback IP, and now you configure the label value. Will it be any label value? Yes, it can be any label value you want within the sRGV. Remember the segment routing global block. Can I do this by hand? Of course, you have CLI to do this. Can I automate this? Of course, you can automate it. So you can rely on tools that you can manage your sRGB block. And anytime you have a new router, you can have intelligence that can grab a label out of the sRGV, and you can assign that to your prefix. Then the next part is you probably will have a service, a VPN. Let's say you have an L3 VPN, or you have an EVPN, or you have an internet BGP route, and those routes will be advertised by 4 with a BGP next hop of 1.1.1.4. Now we stop with the control plane, and now we look at what's happening in the data plane. Device number 1 receives traffic, let's say, for a BGP route that is advertised with the next hop of 1.1.4. My IP to MPLS in position path will make the router number 1 to push the label of the BGP next hop. In this case, will be 16,004. So the packet out of 1 will have the label 16,004. If you look at what's happening at 2, device number 2 is simply going to do a swap, like he will always do. He will do a swap to get the traffic onto the router number 4, because my local label of the traffic coming in is 16,004. I swap it, and now when you swap, you see a very striking concept, which is I'm going to swap it to an outgoing interface with the same label. Now you can see pictorially that your LSP to 4 can be traversing 100 routers between 1 and 4, and they're all swapping the labels to the same label value. So you can jump on any router, and when you want to troubleshoot or inspect an LSP, you will be inspecting by looking at the fib entry for that global label value that you know what it is, 16,004, and the outgoing labels will be completely the same, and then you go to the next router and you inspect the same label value. The label value has global significance. Now 3 is special in the sense that 3 will be acting as a PHP for the LSP. He will simply perform the usual POP, and the traffic will go as IP to the destination number 4. Again, this is a case of global routes. If you were to have VPNs, in the very last step, you will see the VPN label at the top of the stack. And there you go. This is your MPLS data plane. There is nothing new for you to learn when you are doing MPLS today. What we're doing is we're allowing you to remove LDP, removing RSVPTE, and making use of the IGP to signal the LSP. If we had more time, we will take a look at in more detail of the deep dives of all of the use cases. We would have taken a look at TI-LFA for how do I get my 50 millisecond protection with simplicity and pre-computed by the IGP. How will I do network slices with a topic like called segment routing flex algo? How will I work my traffic engineering? How do I assume and how can I deliver intent-based traffic engineering? So traffic that has a particular property can go into a traffic engineer path. And of course, tell me more about this other sibling of SR, which is the B6 data plane of segment routing. But I'm sure, and if you're interested, and if you tell GD about it, I'm sure we can get pretty soon and talk to you about these other topics. In conclusion, I think it's very important that we look at SR as an architecture. You should not look at SR only as, oh, it's an IGP ISIS extension or OSPF. You have to take a look at SR as an industry, as an architecture phenomenon, where you can leverage IETF standardized extensions to the protocols, but then you also evaluate vendors to allow you to understand what sort of local behaviors you get to allow you to simplify even more the intent nature of the traffic forwarding, simplifying the automatic steering of traffic into policies. For us at Cisco segment routing, simplicity is key. And simplicity will always prevail. We are always trying to attack head-on tough problems with simplicity and deliver the solutions. For you to stay up to date, feel free to follow us in social media, LinkedIn, Twitter, Facebook, but most importantly, on the very top, we have an external website called segmentrouting.net, where we have the latest information in SR, demonstrations, TOIs, conferences, references to IETF, references to open source. So please, if you have time, please visit segmentrouting.net. And if you really want to go for your textbook experience, there are a couple of textbooks that we have published, and you can purchase those in your at Amazon and other venues. If you really want to go deeper into the concept of SR, we'll definitely encourage you to take a look at the two textbooks. And with that, I want to send it back to you, Yiri.
Thank you very much, Jose. It was an awesome presentation. So I'm really happy that right now we are covering all the picture of the networking. So we were like talking about the services. Right now we are talking about the transport. And as I mentioned, there is no service without the transport, and there is almost like a useless transport without the service. So they are like coming together. So in the next sessions, we will be also talking about how to really like connect these two together, and we will be focusing on another topic. So if you are interested, please just follow us on this e-vpn.io/flatandlearn. You can also read more about the eVPN and BGP specific things on the e-vpn.io, or as Jose mentioned on the previous slide, on the segment-routing.net. Again, this presentation will be posted like later on the page, so you will be able to read it, and we will also try to post the recording. So one more time, thank you very much, and hopefully see you soon during the next session. Thank you.